Electromagnetic induction. You must be aware of the fact that a current-carrying conductor produces magnetic field around it. Now a question arises, if electric current can be a source of magnetic field, then is its reverse also possible? To verify this, let us perform an experiment. Take a conducting coil connected to a battery and a key placed nearby another conducting coil connected to a galvanometer. Can you tell what will happen if we close the key? Yes, the moment the key is closed, the needle of the galvanometer deflects momentarily. But once the key is closed, there is no deflection in the galvanometer needle. Do you know why? This is because the magnitude of the current has become steady. Now as we open the key, what did you notice? Again, there is a momentary deflection in the galvanometer. Now the question arises, why do you see deflection in the galvanometer only at the time key is closed and opened? At the instant key is closed, a current flows in the circuit which increases from 0 to a certain steady value. Due to the increasing value of the current, the number of magnetic field lines varies. This variation in number of magnetic field lines induces a current in the nearby coil which can be seen by the deflection of the galvanometer needle. Once the current reaches its steady value, there is no change in the number of magnetic field lines and hence there is no deflection in the galvanometer needle. Let us perform one more experiment to verify this result. The setup to perform this experiment requires a conducting coil connected to a galvanometer and a bar magnet having two poles, north and south. Now bring the north pole, N of the bar magnet towards the coil. What did you observe? The needle of the galvanometer got deflected towards one side. Now hold the magnet still. What did you notice? The galvanometer shows no deflection. Can you tell what will happen if the bar magnet is taken away from the coil? The needle of the galvanometer is deflected again, but this time towards the other side. Now, few questions come into mind. Why the needle of the galvanometer does get deflected as the bar magnet was brought closer to the coil and taken away from the coil? Why there is no deflection when the magnet was kept stationary? When the magnet approaches the coil, the number of magnetic field lines linked with the coil changes, which gives rise to an induced current in the coil. When the magnet is kept still, there is no change in the number of magnetic field lines linked with the coil. Hence, no current is induced in the coil. Again, when the magnet is taken away from the coil, the number of magnetic field lines linked with the coil changes and therefore gives rise to induced current. From the above two experiments, we conclude that a changing magnetic field in one conductor induces a current in another conductor. This statement is known as Faraday's law of electromagnetic induction.